supposed to do it. I mean, I don't particularly care about what I'm technically, well, I just know that you care, but I'm technically allowed or not allowed to do it. But it sounds like, so how many people would prefer to have it this weekend as opposed to the following weekend, for example? By this, I mean the weekend indicated on the, okay, how many people would prefer to have it?
Theorem will be the topic of the next lecture. However, today I will start by stating the full spectral theorem, and in there will be some constructions that I will then explain how they're performed. But today we'll only come to the proof, which will then actually just be a corollary from our constructions, of the inverse spectral theorem, best way. I don't know whether you find in literature the inverse spectral theorem. It's rather trivial, but well, that's my regrettable twist here. So in this lecture today, we're going to develop the technology to state and in the next lecture, so that would be lecture 11, prove the spectral theorem. And the spectral theorem has a very simple term. It says for every self-adjoint operator, operator A defined on a dense domain into the Hilbert space we're looking at, there is a projection valued measure. What that is, we're going to make more explicit in this lecture and some more. There is a so-called projection valued measure, and I'm strongly against acronyms, but here, let's call this a PVM, a projection valued measure, okay, because this is so much writing on the blackboard. There is a projection valued measure. What is that? That is a map that takes you from the below sigma algebra over the real numbers, so the sigma algebra that is generated by the open sets into the bounded maps on the Hilbert space, a projection valued measure, and there are certain extra conditions which I'm going to state in a second, such that, well, and for every self-adjoint operator A, so this guy gets the name PA because it's a projection valued measure constructed from A. And how we will construct that, we will learn, such that we can write the operator A in the following fashion, which you will not understand right now, but we will at the end of today's lecture. It can be written as the integral, this still looks good, over the real line, of the identity map on R. I must say that here by identity on R, I mean something slightly more general. I mean the embedding of R into C. So that takes a real number, lambda, and embeds it into the complex numbers, where that's still the identity. Identity R, dPA. Now, you already know how this Lebesgue integral is defined. If the P was not a projection valued measure, but if this were the real numbers or the complex numbers, then you would know how to define this. The only difference is that it now takes values in the bounded maps. I'll explain this nevertheless in detail. That's it. That's the spectral theorem. So here we have this goes into here. This is that. And remember, so this is really just another notation. This is nothing different. We often don't want to write an abstract name for a map here. We rather give the prescription, the function values of the map. And in that spirit, I just give here int R of lambda is just lambda, and then we know that we agreed already for measures to also write this in this fashion. All right? You remember that? So please compare to the lecture on measure theory. In measure theory, this is just notation. This is more often read in the literature than this. However, it's a little clearer. So this is the spectral theorem. And this is invaluable in quantum mechanics, or in fact you can't really do it without the spectrum. Okay, come on. Okay, the spectral theorem. Okay, so now, you see, there is, that sounds terribly non-constructive. It sounds like an existence result, and as it is with existence results, they can be very useful in theory, but they're very little useful in practice, because unless you can construct this PA, given a self-adjoint operator, you know you can write like this, but you would really like to know how to construct these PAs. Now, the thing is, it is constructive. The good news is, but there are only good news, okay? There's only good news. So the theorem is, in fact, constructive. So we will see that from given self-adjoint, that's important, self-adjoint A, we can construct PA along the following three steps. And I did them right now because then we know what the whole thing is about, and then we will start the other way around and start developing the definitions and proofs such that next lecture will be ready to prove that it works like this, okay? But first I give you the application, how it works and how you will use it in practice. Okay, so the first step, step one, you before we construct a projection valued measure, you construct a real valued row measure. What is that? Well, construct a real valued row measure for each psi in H. So we will have one projection valued measure later on. A unique, I should even emphasize, there is in the spectral theorem, a unique projection valued measure. That's important. We associate with every A a unique projection valued measure. Now, the projection valued measures, in order to work with them, we break them down to real valued measures first, but then we have to specify a psi. So the real valued row measure will have the name mu psi, and it will depend on the choice of psi, and we'll construct it for any psi. That's the point. For each psi, what is such a measure? Well, it's a measure that has the name mu psi. It's constructed from psi. It takes a well set in the real numbers, so a measurable subset of the real numbers, and it will produce a real number. That's why it's real valued, whereas this guy was bounded operator valued. Well, we first look at the real valued measure, defined like this, and you know that the well sets in the real numbers, they are actually generated by the half-open intervals. Do you remember? If you know all the half-open intervals, if you know how the measure acts on the half-open intervals, you know how it acts on all of there. Why? Well, because how measures of other well sets can be composed from measures on this, right? Okay, so it suffices to define it on here. So that's the remark, before you get confused, because not every set has this form, but it suffices to prescribe mu psi on these half-open intervals. Okay, it's like in a vector space, it suffices to prescribe a linear map on a basis. Same here, for a measure, it suffices to prescribe the map on this set. Okay, and so now we need to construct this guy from the self-adjoint operator A, because in the spectral theorem, I put an A on the table, and I finally want to arrive at this PA. The first step is to take the A, and you write down the following expression. You take the inner product of the psi with the resolvent of A, which you remember is a bounded operator, if it's defined on the resolvent set. You apply the resolvent to the psi, but the resolvent must be constructed at a complex number. So remember that the resolvent was a map from the resolvent set, which was a subset of the complex numbers, into the bounded operator, so this is recall. Okay, and it was defined by z goes to A minus z inverse, wherever this operator is indeed bounded, which provides the space row of A of complex numbers here. So this is the subset of the complex numbers. Okay, so that's the resolvent. The resolvent, we define this. Remember that the complement of the resolvent set row of A is the spectrum of A. And the resolvent makes an appearance here. Now, for a self-adjoint operator, the spectrum is always real, and here I write T plus I epsilon. And then I take off this expression, which is a complex number, I take the imaginary part, so it's a real number. Then I integrate this whole thing over the real line, over all real T. Now there's the danger, because if there was only R of T and I go over all the real T, I would always hit something in the complement of the resolvent set. Or very often, because I would also hit the spectrum. But if I go away from the real line by epsilon, and I take epsilon, limit epsilon to 0 from above, that means I don't hit the 0. This is defined for every epsilon greater than 0, and I'm sorry, I do not go over the entire real line. I start at minus infinity, and I go only up to this lambda, but then I want to come from the right, so that I have the lambda always included, so I need another limit, delta goes to 0 also from above. And that is it. Okay, so, but this is the Stieltjes inversion formula, and we will see, so here it's terribly ad hoc, of course, but that is what we're going to prove next time, that indeed this measure can be constructed from the A in that way. But you see, in principle, you have everything. You know how to construct the resolvent, you can certainly take inner products, you can take the imaginary part of the complex number, you can integrate up to here, you can take limits, and there you go. That's the mu psi of this interval. Okay, that's it. So there you see how the A goes in. Now step 2, we don't want a real valued measure, we want an operator, a bound operator valued measure, more specifically a projection valued measure. But there's a second step before I construct the PA in the third step. The second step is we construct a complex valued Borel measure from the real one. So for all, or for each psi in, no, for all psi and phi in H. Now we construct a new measure. We have the measure mu constructed with respect to one side. Now I construct the entire mu measure, which in order to properly confuse you, it will also be called mu, and will be called mu phi comma psi. It's another measure, because it has another name. It's called mu psi phi. Psi phi are any elements in the Hilbert space. And this guy, for any Borel set omega, I could again write these guys, but once it's determined, and all Borel sets, okay, we define this guy, and it's supposed to be the complex valued one, and we define it by polarization. So we define it as 1/4 of the mu psi plus phi of omega, you see the mu psi plus phi must be this mu because it only needs one element down here, okay? And it's real valued minus mu psi minus phi of omega plus I times mu psi minus I phi of omega minus I mu psi plus I phi of omega. This is the standard polarization formula, okay? And obviously, if the mu is real valued, this whole object would be complex valued, right? So we have a measure mu phi, which again goes from the Borel sets of R, from the measurable subsets of R, into now the complex numbers. But it's nothing new. It's just we take this one and we write down that one, okay? So you can think how you could have gotten that from here by replacing one of the psi's by phi or so, okay? That's fine, so that's the practical way. And the point is this mu psi comes up very often, but also this one comes up quite often, so it's good to have them both and have them constructed in this way. Okay? So we have the real valued Borel measure, we have a complex valued Borel measure, and that's all of what we want. What we want is a projection valued Borel measure, and that we need to construct now. Before I told you even in detail what a projection valued Borel measure is, as I said, this is just the outlook, although calculationally you can almost do this, okay? But at the end of today's lecture you will certainly be able to do it. So I state the result and the construction in the beginning in order to make you see where we're going. That's the idea. Of course, the problem sheet will have the application of the finite dimensional case. You will cover nice statements like the diagonalization theorem for Hermitian operators of finite dimensional complex Hilbert spaces and so on. Okay, so we finally define the projection valued measure. So step 3, to define the projection valued measure, PA, and it's of course clever to say A is given, from a given A, it's clever to put the A here to remind ourselves that this thing has been constructed from the A, because honestly, that's the only thing it has been constructed from. Because the psi and the phi, you don't choose them, but you have to construct this for all the psi's and phi's, okay? And well, I could write the A up here, but for tradition of this object, it's down here, okay? That's also constructed from there, and we want this PA, and from where to where does it go again? Takes the Borel set in the real numbers, and it maps it to a bounded map. And that's the whole thing. You see, the A, the self-adjoint operator A, but the projections you construct, they're always bounded, and that will really help us a lot. Okay? To define this projection valued measure, simply as follows. You can look at psi, comma, PA, phi. Okay? And we define this as the integral over so the PA eats any Borel set. So this omega comes from here. Omega is an element from the Borel set. Okay? So, yeah. And obviously this is a bounded linear map, it's a linear map. You know a linear map if you know, or at least a bounded linear map, if you know all the inner products here with psi from the left and phi from the right. It's kind of the components, but even more because this doesn't need to be a basis. You know, can construct this for any psi phi. And then here you take as the function, you take the characteristic function of this omega, that is the Riemann characteristic function. This is a measurable set in R. This function is 1 whenever of x or something. If the x lies in the omega is 0 otherwise, the characteristic function, times, but this now is a complex number, so here this is the function, then you just take the complex valued measure. And we know this for all psi phi in H. But thus, we know the map as such. If you know all the inner products, you know the map. Okay? That's it. So you see, from the A here, you construct the real valued Borel measure. From the real valued Borel measure, you construct the complex valued Borel measure. And from the complex valued Borel measure, you construct, now at this guy here, these numbers, but these numbers fully fix these operators and they're most obviously bounded. This guy here is. So that's it. So that's a constructive way. You just need to determine, well, the tricky part is to actually determine this here. And when you do that, you take any self-adjoint operator, you crunch the numbers here, or the functions, whatnot, and you have your projection valued measure. That's it. And in here, everything is actually well defined because you know how to, these integrals I wrote down here, so this should be a white line. These integrals here, this one here, well, this is just a simple real integral. This here is one with a complex measure, but it's defined exactly like for a real measure, okay? That we did in measure theory. It's only that the result, meaning that you can write A as then the integral over the identity on R times dPA. You have to look at that again because that's a little outside the standard definition, but you can already imagine how that works roughly. Okay? So that's the construction. That is what you have to do in practice if you want to spectrally decompose a self-adjoint operator. That's it. Any questions so far? Okay. So after this introduction, we will make all definitions or constructions define what we're talking about, we invert the perspective now. So I introduce like a given A, we have a given self-adjoint operator A, and we construct all these objects. Now we do precisely the other way around. Maybe I should write this down to not confuse you. To this end, we now turn the perspective on the problem upside down. Start from a given projection valued measure P, which has not been constructed from some A. We just say, let's start with projection valued measures and in a sense go backwards. And therefore we will arrive at the inverse spectral theorem, and next time we'll turn it around. Okay? But that's the cleverest way in order to get all the definitions and not lose track of what this is actually good for. Okay? So that's the first section, technical section here. It's projection valued measures. Begins. Definition. A map P that goes from the non-sigma algebra over the real numbers into the bounded linear maps over a Hilbert space is called a projection valued measure, a PVM, if, well, first of all, you want the result for any array set. You want that once it has been mapped, that this bounded operator, P of omega, is actually self-adjoint. Okay. We had this for projections before, or I stated for projections before. I didn't explicitly say by self-adjoint, but I wrote down the formula that stated it was self-adjoint, but at the time I didn't want to use that terminology, if you go back and study that. And then the second statement is that this. So again, for any omega in the sigma algebra, so for any measurable subset of R, it is true that if you apply P of omega and then again P of omega, this is the composition of these bounded maps, that you would again recover P of omega. So that means P of omega is an observable, and that means P of omega is a projection, right? So this is the projection valued part. So this is the projection valued bit of the definition. But then there's more to it. There's also the measure part of it. And that is that if you take P, and if you take the entire real line, which is certainly in the sigma algebra, okay, then you want to recover the identity operator, which is clearly a bounded operator. You want to recover that guy, okay? And the fourth element of it that has to do with the measure bit is that you have an omega in the real sigma algebra, of course, where else? And you can write the omega as the disjoint union. At dot here, and the disjoint union over countably many omega n, could be finitely many, and I emphasize this is the disjoint union. That means that omega n intersection with omega n is the empty set if m is not n. That's the disjoint union. Okay? If you have that, then you can write the sum over all p of omega n, and over all the n's that appear, we write it the same way. Now, even in space equals the p of the omega. And that looks good, right? However, we need a norm to decide convergence should this run to infinity. And you would have to take the operator norm here, and that runs into trouble. So what one does instead, one requires that for any psi in the Hilbert space, this holds psi by psi. So for each psi this holds, and of course it's to be understood like this, and this guy here is of course an element of the Hilbert space for any psi, so this is convergence in the norm on the Hilbert space. Whereas if I took the psi's away, it would be convergence in the norm of here, and then convergence in the norm of the Hilbert space. So also for operators, I wrote this down before, weak and strong convergence for vectors. Well, for operators you have three types of convergence. If you have bounded operators, you can have convergence in operator norm, which is what you would maybe call convergence. Right? It converges using the norm on the space. So that's what isocizing would be. Then we can have this requirement here, which is then called strong convergence for the operator, and we can have weak convergence if you actually come from the left and the side with some size and so on. Okay. Anyway, so this is what it is. We don't need all that terminology. This is the requirement you make, and then actually these two properties here, those are the measure bit of the definition, right? So this says P is a measure because it talks about the domain that happens there to decompose this. And this talks about what the result is, that it's a projection. Okay? So it's a projection valued measure that's any map that satisfies these properties. So here we're not talking about constructing such a map, but first of all saying what we mean by any such map that we call a projection valued measure. Okay? It's actually very straightforward. If I had asked you to define a projection valued measure, and you remember what a projection was from the corresponding lecture, what a measure was, you very likely would have come up with precisely this definition, maybe apart from the yellow bits. Okay. That is what you find when you then work with it, that you actually want it in this way, rather than with respect to the operator norm. Okay? So these guys have a number of properties. A projection valued measure with following properties. Now, first of all, P of the empty set is the zero function on H. So it's a zero function on H, meaning the zero function H takes an element from H into H, and the any element it takes R. Okay, a zero function. The zero function H takes any element on H to the zero in H. Okay, so that's the zero function. We have, this is all very trivial. We have P of the complement of omega is the identity on H minus P of the omega for any omega in the Borel sigma algebra. It's also quite easy to show, of course. Now we have these typical, you know this all from probability theory because we deal with measures all the time. If you have the union of two Borel sets, and then we need to subtract the measure of their intersection, and then you know that this difference is actually given by the sum of the measures of the respective Borel sets. And again, omega 1, omega 2 are Borel sets, and then two more. A little bit more interesting is omega 1 intersected omega 2, we need to be able to calculate this, is actually equal to P of omega 1 after P of omega 2. This is a bit unfamiliar from probability theory, however, here has to be stated. And 5 is if you have one Borel set that happens to lie within another, then you know that the range of P omega 1 lies in the range of P omega 2. Okay. So all of these can be proven. A few lines, the other ones you have to look carefully. On the problem sheet you will be able to satisfy yourself that this is true.
Psi and number 3, right? Einstein.
So you have a omega 1, you have an omega 2. If you think of the measure as the areas, which it is because it's projections, you obviously take the union, but then you miss out one is the intersection, so it needs to be adjusted. Okay. So the remark, it suffices to know, or to determine, or to specify whatever, to know the P's on the half-open intervals like these for all lambda in R, for all lambda in R, because from that you can reconstruct the P of any Borel set, right? It's an argument I gave before, but now we write this down again, and therefore very often people introduce the notation P of lambda. Okay? So it's of course confusing because this P by birth needs to eat a Borel set, and all of a sudden it eats a real number. Now that's obviously a different map. You could call it P twiddle if you want, but you define this way, but you forget about the twiddle, you just know if the P eats a real number, if you find it in the literature or if we write it down, then it's actually just a short form for this guy, which is not too difficult, right? Okay? However, this is called a projection valued measure, PVM, and an object like this, it goes from the real numbers in these projections, and has all the properties that follow from the properties of this P. This is called a resolution of the identity. Resolution of the identity. Because of this resolution of the identity. Okay, so these are different names for virtually the same objects in just a perspective you take. Okay, so don't be confused. If you talk about resolution of the identity, you really can translate into a projection valued measure, because that is what it actually is, what you actually want to look at. So we use this as a shorthand only for this. Okay. There are projection valued measures, and now we use them, you see, because exactly the opposite sequence, like I did for the spectral theory in the introduction, we now construct from the P a real valued, or we could even construct a complex valued Borel measure. So real and complex valued Borel measures induced by a PVM. And again, when I wrote down the spectral theorem, it was the other way around. I could get such real complex valued Borel measure from the H, and then from this real complex value I induce the P, but now we do exactly the other way around. Okay? And that's very simple. Definition. For any psi phi in the Hilbert space, define mu psi phi from the Borel sets of the real numbers into the complex numbers. Let's do it this way around. As now I take the entire Borel set, why not? I write this as mu psi phi of omega, and this is defined as psi, P of omega phi. Okay, so we have an operator, a linear operator. You come from the left and from the right, with the Hilbert space element on the right, that you sandwich it. Okay, and then of course you can complex numbers from it. That's no surprise. And these will depend on what Hilbert space element psi phi you sandwich the operator with. You see, an operator valued measure has much more information than a complex valued measure. So you need many complex valued measures in order to capture the information that before was in the operator valued one. It's totally simple. Okay, this is only to deal with it. Okay, so define this. And well, and then you can also define, of course, so this is defined the complex valued measure. And you can also, for any psi in H, you define the real valued measure. That's now not a big thing. Then psi, if you choose the new psi, you define it as new psi psi. So if you choose the phi to be the psi 2, that's exactly the real valued measure. Where's the real value? It's okay. Mu psi of omega. So this is complex value is clear because the inner product of object with another Hilbert space element with another Hilbert space element is a complex number. But why is this really a real number? Well, this is mu psi psi of that, so that is psi P of omega psi. But because the psi is self-adjoint, this is P of psi psi, right? So this is the property. This is the projection, okay? You have this. And then, of course, this is the same as swapping it again, but now according to a different rule, we're swapping the entries of the inner product. And that's, of course, mu psi of omega bar. And then, of course, that's the proof that mu psi really goes into the real numbers. There it is. Okay. So from the projection valued measure, we construct the other two measures. So there's actually only one thing left. So the entire construction we made is now done from the back. But what we still need to do, we need to give meaning to this integral appearing in the spectral theorem. We have an integral with respect to a projection valued measure. How is that really calculated? How do we really do that? So that's section 3, integration with respect to a projection valued measure. So we need will make sense of integral f dp. Okay, so what is this supposed to mean? Now, it turns out, we can look at this in most mathematics, of course. And we only do this for bounded measurable functions, so we make sense out of this for measurable f. Measurable f, f being here from, so we do go over the real line, f from R to C. So you take complex valued functions, like for instance the identity over R, which is actually more like the embedding of R into C, that appears in the spectral theorem. We want for any measurable function here, we want to make sense of this. Of course, you know the function is measurable if you take the Borel sigma algebra from these two and then prove images of measurable sets are measurable, blah, blah, blah. As long as you would only consider f that are bounded. Now, bounded in the standard analysis sense, that there is a real number such that the absolute value of f never goes above this real number. Okay? Boundedness. That boundedness, of course, becomes boundedness with respect to the supreme norm on the respective Banach space. We'll do that. Okay? As long as you do this for bounded f, this integral operator, integral dp, as it can act on f, is a very nice thing. It's linear, like you expected, that integrals act linearly. The integral of f plus g dp should be integral f dp plus integral g dp, and so on and so on. And we will come there, and actually, it will be linear as long as this f is bounded. That's the good news. And we have a very nice mathematical theory for that, because as long as f is bounded, this guy, which is an operator, because the p is, will be a bounded operator. Everything is fine. The bad news is, we need more. We need to also define this for unbounded f. Because, for instance, already in the statement of the spectral theory, there is the identity map here. So the identity map takes x to x. That's not bounded. Okay? So it's not good enough. And then all hell breaks loose. For instance, you lose the linearity because of domain issues. Okay? And this makes this so complicated. Okay? However, there is no way to avoid this. Okay? Stated it conversely, if you deal with this in a more nonchalant manner, you will miss the subtleties and you will do nonsense. Right? So you really need to look at this. And we do it step by step, so I will point out where the trouble starts. And it's trouble we have to deal with. It's not trouble we can avoid. Okay? Anyway, so this is what we want. We really want to make sense of this. for measurable f, and we go in 3 steps. The first step is to make sense of it for simple f. Do you remember what a simple function was? It was a function that over its domain only takes finitely many different values, and that is where we actually define the whole thing. We make sense of it for bounded f, for bounded functions f, over which we want to integrate, all for a given p, and so far so good. But then here in step 3, we need to make sense of it for unbounded f. Let me call this ABC. I think I call it ABC. ABC, is that right? Yeah. And step C is for unbounded f. We also need to make sense of it, otherwise it's of no use for us. And this is what makes this difference. Okay? Good. Okay. Well, so we could be a little more precise here. We need to make sense of this guy. I write it here again. To make sense of integral over R FTP. So that's what I wrote down before. And I already said that maybe I should write it down. This object, once calculated, will be a map. A linear map. And I said it means linearity. I don't mean that this is no longer linear, but that this thing acting on f is no longer linear. So this will be a linear map. And in fact, as long as the f is simply or bounded, it will be a linear map from H to H. Okay? It will either be a linear map. However, as soon as the f is unbounded, this will still be a linear map, but it will be a linear map. It will be an unbounded operator, so it will no longer be defined on the whole Hilbert space. But this domain where it is defined will of course depend on the operator you have. So it will depend on the operator. So for every unbounded f, this guy has a different domain. Now you understand that if I write down integral f plus GDP, I cannot simply add this to the integral GDP. If I really simply split this into integral FDP plus integral GDP, because the domains don't fit together. You see? That is the problem. That is the problem because the unbounded f will lead to an unbounded operator. Okay? So in this case, for simple f and for bounded f, in both cases, the domain of the operator we're defining here, the domain will in each of these cases be the entire Hilbert space, and there's no problem. And as soon as you go here to the unbounded f, it will turn out that the d integral over R FDP will only be a dense subset, or at least a dense subset, but it will be a dense subset of the Hilbert space, and it won't be the entire Hilbert space. Okay? And that is what makes things a little more troublesome. Okay? But we'll work step by step. We start with a simple f. Okay. Integration with respect to projection values measure over simple f. Okay, and this is really truly simple. So we recall, and it's a slight generalization. If you have a function f from R to the complex numbers, we call this one simple. Well, first of all, we want it to be measurable all the time. Measurable. It's called simple if it has only finitely many values. That is, if I apply f to its entire domain, the range of it is just a finite connection f1 to f capital N of complex numbers. So the f1 to fn are not functions, like usually in a sequence or so. Here I mean by them the function, the finitely many function values for some n and n. So finitely many values. Well, immediately, if this is the case, then the f can be written as a finite sum. That's the whole point. A finite sum of small n from 1 to capital N over exactly the nth value. But where is it taken? So when this is a complex number, it's taken on, so we have a characteristic function, well, on the pre-image of the set of this value with respect to f. So this says f has the value fn wherever it has the value fn. So talk about triviality, okay? So this is this decomposition, and this is exactly the idea